Hey everyone, welcome back to another session with OneClass. Today we're going to be answering some physics questions. My name is Bassam and I'm an engineering graduate. And the physics questions that we'll be answering today will be at the high school and the preliminary university level. Okay, so let's get started over here. Okay, so the first question here that we're asked is how do the speeds v0, v1, and v2 at times t0, t1, and t2 compare? Okay, just give me a second here. Let me just check something real quick. Alright, so we're looking at 5 options and we're trying to figure out which option is the correct answer. So they have a plot down here for us. So looking over here, so we have v0 at the initial of the projectile. So we can see right here the projectile follows this kind of motion, a parabola, and we have v1 on top, and you can see that this vector is a little smaller than this vector. And then v2 over here we have the vector pointing downward, and we can see this is kind of equivalent to this vector. Okay, so one thing to note for parabolas or anything that's going upwards and then downwards, there is a conservation of speed based mainly because of conservation of energy. So at this point when it's initially thrown, all the energy is in the kinetic energy form, and as it goes up, this kinetic energy is converted into potential energy, and then the speed diminishes it, and then as it goes down, the speed accelerates down, and then the potential energy is converted back to the kinetic energy. And we can see here the speed in point 1 is only in the x direction because there's no acceleration in the x and y. It's mostly in the of upward and downward, so in the y-axis, because it's due to the force of gravity. So here we'll look at option A. So here it's telling us v0. So in option A, v0 equals v1 equals v2, which is greater than 0. So all speeds are greater than 0, so that's true. However, we can see that not all the speeds are equal, so we can cross out option A. For option B, v0 equals v2, so speed v0 over here, and then we have speed v2 over here. So that is true with respect to magnitude, but not with respect to direction. And then v1 is less than v0 and v2. So here we can say that this is correct. And since the question is asking for speed, not velocity, speed is measured in magnitude, not in direction. So speed is a magnitude kind of quantity, versus velocity is a magnitude and direction quantity. So we'll mark B correct for now, but let's just double check the rest of the answers. So for C we have v0. So actually I made a mistake. I missed the equal sign. So this is the correct answer over here because it's a greater than 0. v1 is greater than 0 and not equal to 0. So we actually got to say that answer B is incorrect, and answer C, because we have all the speeds are greater than 0, but v1 is less than v0 and v2, and v0 and v2 are equivalent, as we can see in the diagram. So we'll say C is correct. Let's double check D. So for D, we have v0 is greater than v1 is greater than v2 is greater than 0. So we can say that's not true because v0 equals v2. So D is incorrect. And then finally for E, v0 is greater than v2, which is greater than v1. So they kind of rearranged it here, and this doesn't make any sense because we know v1 is not equal to 0. So we can kind of cancel B and E right away. And then looking at the rest, we know that v0 is equal to v2, and then we can see that this one is the correct answer. So we know this is wrong. So we have C is the correct answer. So we'll go scroll down, see at the attempted solution. So from the given diagram, V0 and V2 are same. So we have V0 is equal to V2 is greater than V1 is greater than 0. And this is option C. So the student selected the correct answer. So this is the case of projectile. In a projectile, there are various factors that can affect maximum projectile range, and it follows a parabola. When the projectile is at the highest point of the velocity, at top position is 0, and it increases again when it falls from the top. The horizontal and vertical motion of projectile are independent of each other. So we can see that the horizontal, so in the y-axis, and the horizontal in the x-axis and the vertical in the y-axis, these motions are independent. So here, this answer is correct. Great job. Okay, so we'll mark this solution as correct. Let's clear the board over here for the next question. Okay, so here we're given a true or false question. During any process, the net electric charge of an isolated system does not change. So this is a question about kind of the law of conservation of electric charge. For an isolated system, kind of the definition of the law of conservation of electric charge is that the net charge of an isolated system remains constant, because the charge can neither be created nor destroyed. So this is just the general definition. So this question would require you to kind of just know that as a fact, and it will be true. So here we can say that for an isolated system, so there's no, in some kind of system where we have, positive and negative charge, the net electric charge would never change, because there's no impact from an external environment. So here we say the answer is true. So looking at the presented solution, so they kind of just outlined that the law of conservation of electric charge. So this kind of is important in nuclear reactions. So let me just clear this. So in kind of alpha decay, so when alpha, I guess atom or an alpha molecule decays, that's when kind of you need to understand that electric charge is conserved, and that you add up the correct number of protons and neutrons together. Similarly for beta decay and for gamma decay. So for beta, so there's beta negative and then beta positive decay and gamma decay. But for this question, all you really need to know is that for an isolated system, the net electric charge does not change, and it's conserved based on the law of conservation of electric charge. So, correct answer. Great job. Let's go on to the next question. Okay, so this question is asking, in a collision between two unequal masses, which mass receives a greater magnitude impulse? So it's kind of asking us about a different law of conservation, which is just the law of conservation of momentum. So to think about this, we need to also know kind of Newton's third law. So for kind of every action force, there's an equal and opposite reaction force. So if we had the equation for impulse is as follows. So F1 T1 needs to be equal to F2 T2. So we know because of Newton's third law of motion that for every action force there's an equal and opposite reaction force. So equal and opposite meaning the same magnitude but in the opposite direction. We know that this force will have a negative, and going from there we can kind of take a look at this. So we know, let's say we define there's a final velocity and there's an initial velocity. We would see that if we had F equals ma, we would get m, so initial velocity, or sorry, final velocity minus initial velocity over t, and then this would give us ft is equal to mv minus u, which would be equal to mv minus mu. So, and this, let me just clear up some space over here. So this just kind of shows how kind of the conservation of momentum happens. So here, since we have this equation up here, and since we know F1 and F2 are the same, we know that the total momentum will be conserved for the colliding objects. So let me write out the equation for the first m1 v1 minus m1 u1, so this is for the first object colliding, will be equal to the negative of m2 v2 minus m2 u2. So both the impulses are equal and opposite. So therefore, because that's the case, we know that there's a conservation of momentum. And we kind of just used this equation down here, and we applied it to kind of two objects. So this component is equivalent to this component because of the conservation of momentum, and kind of this equation represents that. So here, which mass receives a greater magnitude impulse is the question. So because the because of Newton's third law, there's an action force and there's a reaction force, and they're equal in magnitude. We know that both kind of masses have an equal impulse applied to them, and there's a conservation of momentum. So that kind of answers that question. So there's no mass that has a greater magnitude than the other. They both have the same impulse applied to them. Okay, so let's look at the attempted solution. In a collision between two unequal masses, which mass receives a greater magnitude impulse? Impulse is also defined as a change in momentum of an object. Impulse, so they show you the equation of impulse, which we have up here. And then m1 v1, so that's the equation. Since the law of conservation states that total momentum remains conserved, or the sum of initial momentum of colliding objects is equal to the sum of the final momentum, so that's the case here. Both the impulses are equal and opposite, thus the impulse is the same for both the objects, which is proved by the law of conservation of momentum. So that's a correct answer. So correct answer. Great job. Okay, let's get on to the next question. Alright, so there's a fill in the blank with 5 options. So the blank of a lens or a mirror is a rotational symmetry axis of the surfaces. So we have 5 options: light ray, paraxial ray approximation, optic axis, focal point, and focal plane. So whenever we think of a lens diagram, it would look something like this. So we have the optic axis, and then we have the lens over here. And then we have, let's say, a focal point F, and intersecting that will be the focal plane. So here we have option focal point, which is over here, and then the focal plane would just be intersecting the focal point perpendicularly. So here it's asking for what is the thing of a lens or mirror that gives you rotational symmetry, or is the rotational symmetry axis of the surfaces. So here we know this lens gets intersected by the optic axis in the center. So we can see how the answer is kind of the optic axis, because if we rotate this around the lens, and the lens will be kind of just, if you think about it, it would be like a convex or concave kind of circular object, or cylindrical object that's either concaved in or concaved out. And it would be rotating around the optic axis. So here we can see that the rotational symmetry axis of the surfaces is the optic axis. Option A just says light ray, so that doesn't really make any sense. Light rays would be like kind of just bouncing off everywhere and kind of bending towards the focal point, or around the focal point based on the object distance and the image distance. Secondly, B, periaxial ray approximation. That's kind of more of a like method rather than describing like the axis, which is what we're looking for. Optic axis is the correct answer. Focal point is just the point, which doesn't really make sense in this situation. Focal plane is just the perpendicular plane over here, which goes through the focal point. So let's look at the attempted solution by the student. So they select the correct answer. The optical axis of the mirror or lens is a rotational symmetry axis of the surfaces. It is an imaginary line that gives the path of propagation of light. In the lens and mirrors, this imaginary axis passes through the center of curvature. Also, it coincides with the axis of rotational symmetry. It is also named principal axis. So yeah, so optic axis and principal axis are the same thing. If a light ray passes along the optical axis, it remains orthogonal to the surface. Then the path will be undeviated. So here, correct answer. Excellent work. And we'll mark that as correct. Okay, let's go on to the next question. Alright, so this question is a chemistry question, not a physics question, but we'll go through it and answer it anyway. So how many valence electrons does hydrogen have? So hydrogen would be, so we know from the periodic table, the hydrogen atom has one proton, so we'll say one proton, and one electron. So knowing this, whenever we kind of look at kind of the question, we want to define some terms here. So what is valence electron? Valence electron is essentially how many electrons are sitting in the outermost shell of any atom. So here we're talking about a hydrogen atom. It could be asking you for another molecule. For a hydrogen atom, it's fairly simple. We have the proton and neutrons in the center, so we have a positive charge in the center. Neutrons don't have any charge. And then we'll have the first shell. The first shell can hold 2 electrons, and in this scenario we only have 1 electron. And since we don't have any more shells after that, so the first shell holds 2 electrons, the one after that would hold 8 electrons. So here we know that we only have 1 electron in the valence shell. So this would be the valence shell. And we have 1 electron in it. If they asked us for, let's say, helium has 2 electrons, which would give you 2 electrons in its valence shell. So hydrogen is the element which has symbol H with 1 atomic number. So they present the correct solution. So here they give helium as an example. Here it has 2 electrons. So yeah, so they present the correct solution. And essentially, whenever you're looking at that, you kind of want to look at the groups about the periodic table, so the columns, and then based on the columns you'll determine how many electrons are in the valence shell. So if we looked at the leftmost column in the periodic table, all the atoms in the, or not all of them, but the beginning ones always have one electron in their valence shell, and onwards, so the second column you'd say would have 2 electrons in this in the valence shell. Okay, so this is the correct answer. Great job. Alright, so we'll mark that as the correct answer. Alright, let's clear the page. Alright, so this question is asking what color light has the highest frequency. So we're looking at highest frequency. So we'll mark that as F. Excuse me. So whenever we want to look at kind of the electromagnetic spectrum and determine that based on kind of the visible spectrum. So the visible spectrum will give us light that is colored. So to a nice mnemonic to know the order of the visible spectrum is Roy G Biv. So sometimes this is with the eye, sometimes it's without the eye, depending on what the textbook says. So here R is red. So R is red. Here I'll make that colored. So R is red. Oh, we don't have an orange. Okay, we'll just stick with black here. So O is orange, Y is yellow, green, blue, indigo, and violet. So to know which side has the higher frequency, you want to flip this mnemonic. So you want to start with the R on the right side, and then O, Y, G, B, I, V, and then how I memorize it is I draw this kind of wave that's small, and then that slowly gets bigger, or not bigger, but has wider wavelengths. So this isn't really a perfectly represented. I can draw a better one here. So here, and then goes something like that. So on the left side, we know that the wavelength is very small, so we have a very small wavelength, and we know at the right side we have a very large wavelength. So just based on looking at this over here, and then because of the equation C, so speed is equal to F lambda. So lambda is wavelength, F is frequency. We know that frequency and wavelength are inversely proportional because of this equation. So we can say that F is inversely proportional to lambda. Therefore, we have high frequency over here and low frequency over here. So let's get back to the question. What color light has the highest frequency? So from our diagram and our mnemonic, so we can see the highest frequency is on this side, and we know that violet has the highest frequency. On the right side is red, and we know red has the lowest frequency. So let's look at the attempted solution. So here, they describe the concept. So using the mnemonic Roy G Biv backwards, since the speed of light for all colors, the variation of wavelength is inversely proportional, so this is correct. The visible light consists of light varying from violet to red, wavelength from 4,000 to 8,000. A red color has the maximum wavelength, whereas the violet has minimum. So that's correct as what we said. So minimum wavelength for violet and maximum for red, and according relationship between frequency and light, they're inversely proportional. And then the violet color has the highest visible colors, is highest in the visible colors of light for frequency. So the solution is correct. So here they also ask what is the lowest frequency. So we already kind of said what it was. It would be so violet for highest frequency and then red for lowest frequency, and that's what they outline. And then second highest frequency over here. So frequency highest in violet, so we know second highest is indigo. And then therefore frequency of indigo is the second highest visible color. So this is kind of a nice way to memorize which color in the visible spectrum of electromagnetic waves has the highest frequency, lowest frequency, highest wavelength, and lowest wavelength. You don't necessarily have to memorize all four of these. Really, you only need to know that frequency on the left of this diagram is highest, right? And then everything else can be inferred based on just this point. So you memorize one thing and then you infer everything else based on the relationship of frequency and wavelength. So correct answer. Great job. So we'll mark that as correct. Alright, let's get on to the next question. Alright, so this is a similar question to what we kind of answered. So the impulse experienced by a body is equivalent to the body's change in what? So to understand what this is, let's define some variables. So we know u, let's say that's initial velocity. So that's initial velocity. Then v is final velocity. And then we know from Newton's second law of motion that F net is equal to ma. And then we can kind of use the definition of acceleration and substitute in the equation over here. So for acceleration, we know that it's final speed minus initial speed over time, and we're going to substitute this into here. So F equals m vu, and this will help us. This kind of derivation will help us explain what the impulse experienced by a body is equivalent to the body's change in what. So going on, we can multiply both sides by t, so F t equals m, and we can expand out the brackets, v minus m u. So we'll clear some space up top. Alright, we have Ft on the left side is equal to mv minus mu. So mv minus mu is just m, because we have the same mass. The mass doesn't change, times the change in speed. And mass times the change of speed is just the change in momentum. So we know that the impulse, which is represented by force times time, so I'll write that over here again. So the impulse, force times time, is equal to the change in momentum. So here our answer is change in momentum. And p, the variable p over here, is representing the change in momentum. And delta here is just change. So change in momentum. So here, impulse is a quantity that is dependent on the applied force and the duration of the force by Newton's second law of motion. So F net equals ma, where m is the mass and a is the acceleration, which is equal to acceleration. So final speed, initial speed over time. They do the substitution and they get that impulse is equal to the change in momentum. Alright, so great job. Correct answer. So we'll mark that answer as correct. And we'll move on to the next question. we'll clear the board. Alright, so let's take a look at this. So the question is asking, how does the average speed of light in glass compared with its speed in a vacuum? So speed of light, usually represented by the variable c, is equal to 3 times 10 to the 8 meters per second. So in a vacuum, this would be the case. So the speed of light would just be 3 times 10 to the 8 meters per second. When it's in a different medium, more specifically in a medium that's more dense, so in this scenario, glass is more denser than a vacuum, or air. So air is a little more dense than a vacuum, but glass is a lot more dense than a vacuum. So usually you will end up with the following equation. So speed of, so let me just redo that. Speed of light is equal to, so the speed of light in the medium is equal to the speed of light in a vacuum divided by some index of refraction. So this index is represented by n. For denser mediums, that will be greater than 1. So in a vacuum, the index of refraction is just 1. In mediums like glass, it would be greater than 1. So we know for a fact that it will just be greater than 1 for glass. So we can look up the exact value. So here we can see from just the number provided here that the exact value is 1.5. We don't necessarily need to know that to answer this question, but for most materials that are denser than vacuum, so all of them have a refractive index greater than 1. So what this means, if we increase the bottom compared to what it would be in a vacuum, the speed over here would decrease because we're increasing the denominator, and we'll end up with a smaller value for speed. So right away we can kind of see that for a denser material like glass, we would have a lower speed of light when compared to the speed in a vacuum. So that's kind of the answer to this question. So the speed will be decreased or less than what it would be in a speed in a vacuum. And we can use this equation to calculate it if we were given numbers in the question. So let's look at the attempted solution by the student. There is a change in the speed of light when it travels from one medium to another. In glass, this would be less. And they go on to describe why that's the case due to the refractive index. Excuse me. And then the refractive index for glass is 1.5, approximately. So for a denser medium, the speed of light changes and it will be slower. And then for a rarer just means less dense. This happens when there's a change in medium. So whenever there's a change in medium, there will be a change of speed. So if you were going from glass to a vacuum, the speed would increase. And if you were going from vacuum to glass, the speed would decrease. Okay, so we'll mark this as correct answer. Great work. Alright, let's mark this as correct and move on to the next question. Alright. So the next question, okay, so I forgot to number these, so this is question number 9. So for the next stream, I will be numbering these questions just so you can keep track of these questions as I go along through them. So this is question number 9. So it's asking for which end, north or south, of a bar magnet do magnetic field lines emerge. So you can just draw a standard bar magnet, something like this. We'll have a north end and we'll have a south end. So this is a matter of knowing kind of does the direction of the magnetic field lines come from the south end or does it come from the north end, and what does it look like? How does it look like? So what it looks like will be something like this. So it would come out from the north end. So So I'll draw arrows here, and it will enter the south end. So the magnetic field line will come out of the north end and will enter the south end. So it'll have maybe like, so it'll be a bunch of these. I'm just drawing a couple to show you the direction, but it'll be just a bunch, kind of a bunch of lines. So just a magnetic field around this magnet, and it would also come around from both sides. So, but it'll always be coming out of the north end and will be coming into the south end. And I'll just have like a bunch. So this is kind of just to help you, based on the question. So a more complicated question might use this to plug in some values and give a direction of the magnetic field from for a magnet. So here for a bar magnet, the magnetic field comes out from the north and enters into the south. So let's look at the attempted solution by the student. The answer is the magnetic field lines of a bar magnet form closed loops, so that's correct, that emanate or exit from the north end of or pole and terminate or re-enter in the south end. So this is the correct answer by the student. So correct answer, great job. And we'll mark that as correct. Alright, so the next question, if you comb your hair and the comb becomes positively charged, then your hair becomes what? So if we have a comb, so it looks something like this, and maybe it has like a bunch of spikes, and you're combing, your hair. Maybe you have long, luscious hair and you're combing it. So here we know that the comb becomes positively charged. So we know there's a positive charge on the comb. On the hair, what kind of charge are we getting? So you really only have three options that you can answer here, either positive, negative, or I guess neutral. So no charge. So whenever you're rubbing two materials on each other, you're going to have a transfer of electrons. So there won't be a transfer of positive charges. It will only be a transfer of electrons. So here, because we have a positive charge on the comb, in order for this to happen, electrons need to be moving from the comb into your hair. So we have a bunch of electrons just from friction forces. They're moving from the comb, entering your hair, and you're getting that positive charge on the comb. So because you're adding more electrons to your hair, and your hair would initially be just neutrally charged, your charge is going to be negative. So you're going to get a negative charge in your hair. So that's kind of the way to think about it. So for any materials, you're trying to think about how is the electron transfer occurring. Since we end up with a positively charged comb, we'll end up with a negatively charged hair. So when two objects come in contact with each other, then due to changes in electric charges, positive charge is built up in one object and negative in the other. This is also due to the build of static electricity. When hair is combined, then the unwanted electrons from hair go into the comb, and hair acquires a positive charge. Now both hair and comb attract each other. After combining, the comb becomes negatively charged because each material has a tendency to lose or gain electrons. So here they kind of have it backwards. So if you comb your hair and the comb becomes positively charged, then your hair becomes negatively charged. So here they say when hair is combed, then the unwanted electrons from the hair go into the comb, and hair acquires a positive charge. See, that wouldn't really make sense because here we have a positively charged comb. So correct thought process, incorrect answer, mixed up hair and comb, it should be the opposite. The comb is positively charged. Sorry, becomes positively. So becomes positively charged. Therefore, your hair will become negatively charged. So the answer is correct. The thought process is correct, but the answer is just mixed up. So it's just the answer should just be the opposite. So let's keep going to the next question. So the previous question was question number 10. We're going to question number 11 now. So I just need to get into the habit into numbering these questions. So question number 11 over here. So when a boxer moves away from a punch, he's trying to reduce the impact of the punch. Oh, sorry, I'm reading the answer. So the question here, when a boxer is moving away from a punch, the force experience is reduced because. So we have kind of, let's say someone is getting, like a boxer has a giant fist. Let's say this is a fist. So this is just a bad drawing. Let's just say it's a fist with some force that punches the boxer. So the boxer moves away, and the force is reduced. And we need to answer, why does this happen? So we want to look at the equation for momentum and impulse. So Ft equals m delta v. So here we know the mass is constant, and we know that these are kind of the two variables, so force and time. So to decrease the force, essentially when the fist makes contact, there's two variables that you can use to determine the impulse. There's the force and the time, and those are the only two variables that you can kind of manipulate or to get a different get like the same impulse, but to change kind of force, increase force or decrease force. So here what the boxer is doing, he's increasing the duration of the punch. So he's moving away. There's still contact to the boxer, but he's just moving away, so the time of the impulse is decreased. So we know in this situation time is decreased. The impulse doesn't necessarily change, it's just that the time is decreased. Sorry, time is increased. I have that backwards. So because he's moving away, time is increased, and the duration of the impulse or the impact of the fist to the face will increase. And because this is the case, and we know that the impulse will, so we have to conserve the total momentum. So law of conservation and total momentum. So the total momentum will be conserved. So this side of the equation is constant. And that means this side of the equation has to also be constant. So knowing this, we know that the time has increased. The only way to keep this side of the equation constant is for force to decrease. So force needs to decrease for us to obey the law of conservation of momentum. So this kind of describes why the force experience to the boxer is reduced. So mainly what the boxer is trying to do is increase the duration of the impact of the punch. This increases our time variable, and thus that decreases our force experience, because we have the law of conservation of momentum, and we know that this side of the equation has to remain constant. So let's look at the attempted solution. When a boxer moves away from a punch, he's trying to reduce the impact of the punch's force by increasing his impulse. To conserve the total momentum, as we know, impulse is equal to change in momentum, so there's the equation we're looking at. By moving away, the boxer increases the time of the impulse, which reduces the impact of the punch. So this is the correct answer. Great job. Let's go to question number 12. So question number 12. So in this question we're given a diagram and we're given two masses, and the question is asking, in the given figure, a block of mass m in the following figure slides on a frictionless surface. So here there's no force of friction, it's a frictionless surface. So let's just draw a quick diagram and then we'll continue the question. So we have some frictionless surface, and it's kind of something like this. And then derive an expression for the tension in the given string. Give answers in m. So the bottom mass, m, and then the upper mass, capital M, as constants. So we have to start off by drawing free body diagram. So I'll erase this diagram, but we'll start off with the top mass to draw the free body diagram. So for this mass, we'll just put a dot in the middle, and the force that's moving this is the force of tension. So because it's tied to a rope, we know the force of tension is pointing the positive x-axis. So I'll draw a little coordinate diagram. So the x is positive in this direction and y is positive in this direction. So that's the first component of our answer. We know Newton's second law of motion says F net is equal to ma. So we know here Ft, so the net force is just Ft. Mass, capital M, because we're looking at the mass up here, times the acceleration. So we have some acceleration. We'll call this acceleration in the x. So we'll call this acceleration in the x direction. So we'll call the acceleration for mass m, acceleration in the x, and acceleration in the y for mass, lowercase m. Okay, so that's the first free body diagram. For the second free body diagram, we have, I'll draw it over here. So let's see if I can, yeah, I'll move this over here. And I'll draw the second one over here. So we have this mass over here, and then we have the force of gravity, so Fg, and then we have the force of tension, Ft. Because the rope is connected, we know that the force of tension here and the force of tension here is the same. Okay. And then we'll use F net equals ma to derive the second equation. So we know the acceleration here is downward. So acceleration in the y is downward. So we know Ft minus Fg. So this is the net force in this free body diagram will equal mass, so lowercase m, times acceleration in the y, and it's in the downward direction, so we'll put a negative sign in the front. So now we have two equations here. We can go further to say that Ft minus mass times the force of gravity, so or acceleration due to gravity, which is just represented by the variable g, which is 9.8 meters per second, is equal to negative a. So here I have a, so it's a, let's just say ay. So we know ax will equal ay because the rope is connected here. So we know if lower mass accelerates, we know this mass will also accelerate at a similar acceleration. So we'll just represent this by a, so no subscript. So we'll just erase the subscripts because we know they're the same. So we'll erase this, and we'll erase this, and we'll get rid of this. Alright. So knowing this, we can rearrange this equation, and we'll end up with Ft over m equals a. And we'll use this, and we'll substitute it into that. So we'll substitute the value of a into that. So we'll have Ft minus mg equals negative m, and then we have ft over capital M. Okay, so we've kind of we're getting closer to an equation that we can use to represent the equation with kind of ft. So we want to derive an expression for the force of tension. So we're trying. That's our end goal here. So we want to isolate for ft. So we'll bring the ft components on the left side, and we'll take everything else to the right side. So we'll have ft plus. So we have this part. We're going to move it to the left side. So plus m over m ft will equal, so we'll move mg to the right side, mg. So I'll erase the top part. To make some space. So now we'll factor out ft, that'll give us 1 plus lowercase m over capital M, which will equal mg. And now ft will equal mass times gravity. So gravity is just 9.8 meters per second over 1 plus m over m. So here we've essentially given in our answers. So here give answers in m, lowercase m, capital M, and constants. So g is just a constant. We know what the value is. And then we have the rest, m on top. And then we have 1 plus m lowercase m over capital M. So we've provided the derivation for the force of tension with kind of those variables. So let's look at the attempted solution. The vertical forces for block 1 are balanced, and thus writing the equation for the x components. In the case of block 2, the situation is different as subject to gravity and tension. So f at x, so for the first mass, they derive the equation, and they represent t here as the force of tension. We have ft, so it's just the same variable. And when the block m moves to the right, then the expression for block m, the lowercase m, can be written as follows, and that's kind of what we derived. And then they end up with tension. So they do the same substitution and the same manipulation of the equation to get to the final answer. So this answer is correct. So correct answer, great job. So we'll mark that as correct. Alright, so thanks for tuning in to this session. Hopefully you found this session helpful and learned how to solve some popular physics problems. If you have any more questions or need any more homework help, you can always go on OneClass.com, and you can always visit the link in the description. If you enjoyed this video and you want to see more content like this, you can click the subscribe button and give a like for this video. I'll see you in the next session. Goodbye for now.